All right, so we're going to continue our discussion on noise in MEMS by first talking about the equipartition theorem. So the equipartition theorem of thermodynamics states that the average thermal energy for each degree of freedom in a system is W for energy, 1/2 Boltzmann's constant times the temperature. So as expected, as temperature increases, the average thermal energy will increase. We're going to define a degree of freedom as so I have a degree of freedom is defined as being capable of storing energy independently of other variables. Independently of other variables. So thinking about things from a circuits context, this would be if you had an inductance that could not be combined into an equivalent inductance with any other inductors, that would be 1 degree of freedom in your system. For each capacitor that you cannot combine down into equivalent capacitances, that adds another degree of freedom to your system, and so on and so forth. So as a couple of other examples here really quickly, we could say that an ideal gas molecule has 3 degrees of freedom. Um, which would be the velocity in the x direction, the velocity in the y direction, and its velocity in the z direction, right? Because it will have kinetic energy terms associated with each of those 3 directions. If we had a simple harmonic oscillator, which we're going to be dealing with a little bit later when we talk about accelerometers, they have 2 degrees of freedom. So this would be the velocity of the proof mass as well as the position of the spring. So some kinetic energy as well as some potential energy. So we're going to use the equipartition theorem. And we're going to talk about thermal noise in electrical systems, and thermal noise in mechanical systems. So as I mentioned a moment ago, in an electrical system, the number of degrees of freedom is simply the number of independent inductors added to the number of independent capacitors. So for an independent inductor, we'll have an average thermal energy, W subscript L, of 1/2 the inductor value times the RMS value of the current squared, which will in turn be equal to 1/2 kBT. And so from this, we could say that the RMS noise current of an inductor is going to be the square root of kBT over L. Very similarly, for an independent capacitor, our energy stored will be WC is 1/2 C times the square of our RMS noise voltage, which will also equal to 1/2 kBT from the equipartition theorem, giving us an RMS noise voltage of square root of kBT over C. Now, resistors are not capable of storing energy. However, they essentially work as a white noise generator in our system. Okay. So we'll say that resistors have a power spectral density of Vn squared with a bar over it of 4 kBT times the resistor value itself. So looking at this equation where this R could be representative of an equivalent resistance of a system, essentially if we put resistors in parallel, we're going to wind up lowering the amount of noise that's generated by our resistors in our system. And if we put them in series, we're going to wind up increasing the amount of noise generated in our system. Okay. Moving on to our mechanical systems. You can say that in a mechanical system, um, the total average thermal energy will be equal to the sum of the kinetic energy in the system and the potential energy in the system. So let's say that we have a simple harmonic oscillator, something akin to this. Okay. So here's my anchor point over here. And let's say that I have some sort of proof mass like so. Mhm. There might be some sort of spring having some spring constant K that attaches our proof mass to the anchor point so that whenever this proof mass, let's say, experiences some form of force, pushing it either to the left or to the right, that proof mass will have kinetic energy and our spring will have some amount of potential energy. Okay. We might also have some sort of damping in our system, which I'm going to represent by an object here that looks like a damping system, but this could be representative of the friction in the system, all that kind of good stuff. And our damping coefficient is going to be gamma. So looking at this simple spring mass damper system, which a lot of the microstructures that we're going to deal with in this class can be treated in this way, we can say that um, we're going to take a look at the kinetic energy will be, I'm going to write this as W kinetic 1/2 mass times velocity squared, where I'm not going to use the symbol V for velocity here. And when we talk about, sorry, brain fart here, accelerometers, excuse me, in a few minutes, you'll see why. Instead of giving this a symbol V, I'm going to say that the velocity is the first derivative of the position of the mass, right? So if our mass has some particular position in the x-axis, then the velocity is going to be the derivative of x with respect to time, which I'm going to represent as x dot. And so this is going to be our RMS noise velocity squared. And from the equipartition theorem, this will be equal to 1/2 kBt, which tells us that our RMS noise velocity in mechanical systems will be the square root of kBt over m. And the potential energy in the system is going to be W potential. This is provided by the spring. So we'll be dealing with 1/2 our spring constant, K, times our position squared. So energy stored in the spring will be equal to 1/2 kBt. And rearranging this, we find that our RMS noise displacement is going to be the square root of kBt over K. And I just want to be really, really clear here. So I'm always going to try to use the symbol KB to talk about Boltzmann's constant, and K usually without a subscript to talk about a spring constant, because obviously those symbols are very, very close to each other. Whenever I do use a subscript on the K for a spring constant, I usually use lowercase letters to indicate the type of spring system that we have, right? So when we're talking about an extension rod spring, I use lowercase e for the subscript. A guided beam spring was lowercase gb. So I'm going to try to make it as obvious as possible when I'm talking about Boltzmann's constant versus spring constant, because reusing these symbols can definitely get confusing. Just anecdotally, the gentleman that wrote the textbook where I'm getting some of these notes from, Dr. Vili Kajakari, he used to be a professor here at Louisiana Tech. And so he would buy me a Subway sandwich for every time I could figure out where he had ambiguous symbols. So I ate for free for pretty much a quarter, helping him proofread his textbook. So I'm going to try to be as obvious as possible here. All right, so if we look at this conceptually as kind of equivalent-ish to what we would see in our electrical systems, right? We have our energy storage elements here, our proof mass, we have that has some RMS noise acceleration. We have our spring, which has some associated RMS noise displacement. Well, up here in our electrical systems, we also identified resistors, our third component, as acting as a white noise generator in our system with this particular power spectral density. Well, as it turns out, in our mechanical systems, we're going to have an analog to this as well, and it has to do with that damping coefficient gamma, okay? So our damper is going to essentially serve as a noise force generator in our system. How did I write this up here? Such that damping will have a power spectral density of F sub n squared with a bar over it will be 4 kBt times our damping coefficient of gammas. Right. And we'll go into much, much more detail about damping, specifically at the micro scale, later on in this class. Okay. So the last thing that I want to talk about with regards to noise is going to be the concept of input referred noise, and then a few things that are associated with that. Okay. So let's talk briefly here about input referred noise. So I'm going to draw a simple block diagram here. Okay. I've got some sort of system, drawing it as if it were an amplifier. We'll sort out at that in a moment. With a gain of A, input signal, whatever that happens to be, is on the left-hand side. Output signal, whatever that happens to be, is on the right-hand side, right? So let's say that this is a voltage amplifier. Okay. So if our voltage signal is 10 microvolts and our amplifier stage has a gain of 100, then what we would expect to see here at the output would be 10 microvolts multiplied by 100, which would be 1,000 microvolts or 1 millivolt. Okay. But very often we're going to observe some amount of noise voltage at the output of our signal as well, right? So because of the amplifier itself, we might also see what I'm going to say is VRMS out is, let's say, 10 microvolts worth of signal here. Okay. So we see, like, we're able to measure this voltage at the output of our system. But this is kind of an unfortunate place to consider it when we are analyzing the characteristics of our system as a whole. So generally speaking, we would refer this output voltage or output noise voltage to the input of our system so that we can compare the noise level to our input signal to see whether or not we'll be able to accurately measure the input signal of interest, right? And that would be quantified by signal noise ratio and those kind of good things that we'll talk about here in a moment. Okay. So what we could do instead, okay, is kind of change our frame of reference for this system. So we'd still have our input signal here. V sig is going to be equal to 10 microvolts. And we're going to treat this as if it's fed into a summing block, right? And then we're going to have our noise signal here. So this is going to be VRMS in. So this will be our input referred noise voltage. We'll sort out what our mathematical expression for that will be in a moment, but it should be fairly obvious. Both of these signals get fed into our amplifier, having a gain of 100. And what we should see is the exact same output. So we'll have our desired output of 1 millivolt as well as our undesired output of 10 microvolts of noise. Okay. So how we're going to get our input referred noise voltage is literally the easiest thing that we can think of. We're simply going to take our output noise signal, divide it by the gain, and then move it over here to the input side, right? So this would just be VRMS out over a factor of the gain. Using the numbers from this example, we would have 10 microvolts divided by 100 would be 0.1 microvolts. And now we can easily see that our signal is 100 times greater than our input referred noise. So we shouldn't have any issue whatsoever in accurately measuring our input signal, or being able to differentiate the real part of our output signal and the contribution from noise on our output signal, right? So if we were to have a multi-stage amplifier, so we had a situation like this where we have multiple gain stages. So let's say that this stage has a gain of 1. Here's our input for this stage. Here's our output for this stage. So the output of stage 1 will be fed into the input of stage 2, like so. And then here's our output of stage 2. So I'm going to label this as VRMS out 2. The signal right here will be VRMS out 1. And our total input referred noise, VRMS in, for this system is going to be the square root of VRMS out 1 squared divided by A1 squared plus VRMS out 2 squared divided by A1 squared times A2 squared, right? So we're essentially taking the output noise voltage from stage 2, referring it to the input of stage 2, and then referring that to the input of stage 1, which is why we have the square of both the gains for the signal on the far right-hand side. If we had 3 amplifiers like the homework problem that you guys are going to get, you'll do it over all 3 gain stages, but it's very, very easy and straightforward, right? This concept can be applied to systems outside of electrical systems and all of that kind of stuff as well, just for what it's worth. And we'll explore that more in a little bit. All right, so I mentioned the concept of signal to noise ratio. So we're going to talk about that as well, just so that everybody's catching what we're throwing here. So our signal to noise ratio is defined, SNR, as the ratio of signal power to noise power. So we could write that as power of the signal over the power of the noise, or the RMS value of our signal squared divided by the RMS value of our noise squared. Okay. Now, usually, this term is actually expressed in units of decibels. Okay. So our signal to noise ratio using a decibel scale, SNR dB, is going to be 10 log base 10 of these ratios, right? So that'll be our signal power over our noise power, or 20 log base 10 of the RMS value of our signal over the RMS noise voltage of our signal. Where getting rid of the square on the voltages is how that we get multiplied by a factor of 2. Okay. So the signal to noise ratio characterizes the signal quantity, and we can use this along with the input referred noise as a means to quantify the noise of our system, right? So in this previous example here, we had Vsig of 10 microvolts. The input noise signal was 0.1 microvolts. So the ratio of Vsig over Vn was 100. So that would be 40 dB signal to noise ratio, right? So 10 times an SNR of 10 would be 20 dB, an SNR of 100 would be 40 dB, and so on and so forth. All right, so these are the various noise-related quantities that I wanted to cover. We'll use them as we go throughout things. So we've got 30-ish minutes remaining. So let's start talking about accelerometers. So, oh, I spelled that really bad. So I want to provide you guys with a little bit of context here and kind of explain how the class is going to go. Not just this class, but kind of the remainder of the quarter, okay? So we're going to talk about accelerometers because they are one of the most widespread MEMS devices in utilization, okay? So accelerometers are everywhere. I think I mentioned this on the first day of class, but we have several of them in our phones, they're in our cars, all of that kind of good stuff, okay? So very, very widespread utilization. Now, in its most basic form, an accelerometer is a mechanical harmonic oscillator system, okay? And that's how we are going to approach it. However, realizing that simple harmonic oscillator can happen in a variety of different ways, and we can measure acceleration experienced by the proof mass in these systems in a variety of different ways, depending on if we are using capacitive sensing, piezoelectric sensing, piezoresistive sensing, and so on and so forth. So we're going to talk about accelerometers today from a very, very general standpoint of understanding how they work. And then we're going to use this device as kind of a reason to get a better understanding of the different types of sensing mechanisms that are employed in MEMS systems so that we can refer back and have an idea of how the system as a whole works. So that's kind of the methodology that we're going to go for. And then once we get into other things, we'll talk about pressure sensors and then use that as a vehicle to talk about various things. Gyroscopes will allow us to talk about actuation as well, capacitive thermal, all of that kind of good stuff. So we're using these specific devices as kind of a framing structure to explain why we're going to talk about the different types of sensing and how it's applied, or the different types of actuation and how they're applied. Okay. So redrawing my simple harmonic oscillator system from before, something akin to this. I'm drawing a box here. Like so. Bless you. And this is going to be the frame of our system. Okay. Then inside this frame, I'm going to have a proof mass. Symbol will be M again. Connecting my proof mass to my frame will be some spring, having a spring constant K, and my proof mass might experience some form of mechanical damping through friction, air resistance, etc., that I'm going to quantify with some damping coefficient gamma. So we're going to assume in this first case that our proof mass is only able to move in one direction. So I'm going to define a proof mass displacement x sub m like so. And our frame may move as well. So I'm going to have a frame displacement xf. So let me just annotate this really quickly. So m represents our proof mass. K represents our spring constant. Gamma represents our damping coefficient. And xm represents our mass displacement. And x sub f represents our frame displacement. And so what we should see in a system like this is that when the system as a whole experiences some form of acceleration, we're going to confine that acceleration to be in the x direction along with everything else here. We should see that if our frame experiences some acceleration in the x direction, it's obviously going to move in the x direction. Our proof mass is also going to move in the x direction, but we should observe that our proof mass's movement lags our frame's movement because our spring and our damping system is going to kind of, I guess a better way to put it would be the inertia of the proof mass is going to try to keep it in place. And then the spring and the damping are going to attribute to how it moves and how long it takes to move after the frame itself has experienced that acceleration. Okay. So the equation of motion for this system will be as follows. Okay. So we're going to say that this is going to be essentially a sum of forces here. So we're going to say that our proof mass times the second derivative of our mass displacement with respect to time plus our damping coefficient times the derivative of the difference between our mass displacement and our frame displacement with respect to time, plus our spring constant times the difference between our mass displacement and our frame displacement will be equal to our force. And I'm going to label this as F sub E for right now, where F sub E is the external forces acting on the mass. Now, we can see very easily that the middle term and the rightmost term on the left-hand side of the equal sign is dependent on the relative position of the proof mass with respect to the frame, right? So we're taking the difference of those. So we're going to make that leftmost term, which is the odd man out, look more like those two other terms by subtracting the mass times the second derivative of the frame displacement from both sides. So if we subtract that term from both sides, this equation will now look like this guy. So we'll have mass times the second derivative of xm minus xf with respect to time plus damping coefficient times the first derivative of xm minus xf with respect to time plus k times xm minus xf will be equal to our external forces minus m times the derivative, or excuse me, the second derivative of xf with respect to time, where what we have over here is the inertial force on the frame. And this guy right here is once again still just the external force. So this is just the sum of our forces. So we're going to simplify this expression even further as mass times the second derivative of displacement plus damping coefficient times the first derivative of our relative displacement plus spring constant times our relative displacement is equal to our total force. Okay. So this is our equation of motion for a simple harmonic resonator. And we can now use Laplace transform to analyze this system. Okay. So if I want to know what my displacement is, so let me just write this down here. So using the Laplace transform, with the following initial conditions. And our initial conditions are going to be, we don't have any energy stored in the system to start with. So that would be our displacement is going to be 0 and our initial velocity is going to be 0. We could rearrange this expression and solve for f, right? So we would get s squared mx plus s gamma x plus kx is equal to f, where the second derivative is where the s squared comes from, the first derivative is where s comes from, zeroth derivative doesn't have an s term. Rearranging this guy, we would then see that our displacement, x, is simply going to be our force divided by s squared times m plus s times gamma plus k. Okay. And what we're going to do now is we're going to define the resonant frequency of the system. So omega naught will be the square root of K over M. So spring constant over mass. And the quality factor of our system will be omega naught M over gamma. Using these two terms, we can rewrite our expression as follows. Okay. So taking this a step further, having this exact same expression. So I'm going to divide through the numerator and denominator by mass, okay? So we would have force over mass, okay? So that gets rid of the m from my s squared term. And now I have gamma over mass, right? So gamma over mass is looking kind of similar-ish to the reciprocal of our quality factor there, okay? So, but I have an extra term of omega naught. So I'm going to write this as S times omega naught over Q, right? And when I have K divided by M, well, that's so the square root of K over M is omega naught. So K over M without the square root is going to be omega naught squared. Okay. Lastly, recognizing that the force divided by the mass is just acceleration because F is equal to ma, we can see that the relative displacement is related to the acceleration experienced by the system. X dot dot over s squared plus s omega naught over q plus omega naught squared, like so. And so from this, we can say that our transfer function from our system and I'm going to put in note here, frequency response, because since we're in the S domain, we can easily convert this over into the frequency domain by just saying that S is equal to J omega, right? Will be H of S is equal to our output, which is our relative displacement, divided by our input, which is our acceleration. And so that's just going to be 1 over S squared plus S omega naught over Q plus K. And so since omega naught and Q are dependent on the mass, the damping coefficient, and the spring constant, we can see now that all three of those factors play a role in how quickly our system responds, the amount of displacement we get for a given amount of acceleration, all of that kind of good stuff. Okay. All right, so now let's talk about our low frequency response. So when the frequency of excitation, omega, is much lower than our resonant frequency, and I'm going to make a note here. That this is our excitation frequency, so that not trying to make sure we understand the difference between omega and omega naught, right? Omega naught is a fixed frequency that's dependent on the system itself. Omega is just the frequency that we are subjecting this system to, right? So when omega is much lower than omega naught, then our equation for our displacement is going to reduce, right? So what I'm going to do here is I'm going to substitute in S is equal to j omega. So our acceleration stays the same. S squared is going to look like j omega times j omega. So j times j is -1. So we'll have minus omega squared. Okay. Now, replacing S with j omega, I'm going to have j omega times omega naught over Q. And then lastly, I'll just have omega naught squared here, right? So when omega is very small compared to omega naught, those first two terms in the denominator are essentially not going to really do anything, right? The omega naught is inherently going to be significantly larger than either of those two terms. So we can see that our displacement will be very close to simply the acceleration experienced divided by the square of the resonant frequency. Okay. So what this relationship tells us is that when we excite our system or when we're experiencing accelerations that are much, much lower than our resonant frequency, we can actually scale down our system um, without perfecting its performance by reducing the spring constant and the mass proportionally. So this is essentially why MEMS accelerometers can exist, okay? As long as we excite them much, much lower than the resonant frequency, or another way to think about that is as long as we design them such that their resonant frequency is at extremely high frequencies, so that, when we get into a collision in our vehicle, those accelerations experienced are going to be at relatively low frequencies in compared to that omega naught. We can get a device that actually works, okay? That being said, our thermal noise vibrations are going to increase as our mass is reduced. So let me just go back here really quickly to our notes on mechanical noise, right? So if we look at our RMS noise acceleration up there, right, we see that the RMS noise acceleration is equal to the square root of our thermal voltage divided by our mass. So if we make our mass smaller to try to make our system smaller and all of that kind of stuff, it's going to make our noise voltage, or excuse me, our noise acceleration look larger. So there is a trade-off and there is a limit to how small we can make our systems before our noise is larger than the signal that we're actually trying to measure. Okay. So just wanted to point that out to you guys. So this is what our low frequency relationship is like. At very high frequencies, So when omega is much greater than omega naught, we're going to have something that looks akin to this, okay? So here's our x. So I'm taking the acceleration, which is the second derivative of our displacement. So that would be s squared x in the numerator. Well, s squared is going to be negative omega squared again. I'll have negative omega squared divided by negative omega squared plus j omega omega naught over q plus omega naught squared, right? When omega is much greater than omega naught, this simplifies to omega squared over omega squared. Actually, sorry, there should have been an x up here. So we have a situation essentially where x is equal to x. Okay. Obvious, but what does that mean? Okay. Essentially, what it means is that our proof mass isn't moving and we're only seeing the frame move. Okay. So at extremely high frequencies, okay, we don't actually get any good relative displacement because the whole system is moving. Another way to think about it is that we're oscillating things so fast that the system doesn't really have time to ever respond or change to anything. So this implies that the mass that we're using is actually too large for our system. And since we're talking about MEMS systems very specifically, we practically never ever develop a system where it's designed to be excited greater than the resonant frequency. So this relationship right here would be more akin to how macro scale accelerometers are used to measure seismic vibrations and stuff like that. So for the intents and purposes of this class, this is the relationship that we are going to wind up using. Okay. So we've got a little bit of understanding about how this system is going to behave in the frequency domain. So now let's talk about it a little bit in the time domain. So in the time domain is where we're really going to see how damping plays a factor in our system's behavior. Okay. So if we look up here really quickly, we can see that our damping coefficient is inversely proportional to our quality factor. So if Q is equal to 0.5, then our system is critically damped. In a critically damped system, Um, we get the fastest possible response time without overshoot or ringing. If our quality factor is less than 1/2, then our system is considered to be overdamped. So in an overdamped system, we have a slow response time with no ringing. So this is a useful property to have. Unwanted vibrational modes. And resonance in devices with multiple degrees of freedom. Finally, if Q is greater than 0.5, then we say that our system is underdamped. Um, where in an underdamped system, we have a very fast response time with ringing and overshoot. So I'm going to draw a picture here just to kind of show what the differences between these things are. So this will be time on this axis, and let's say we'll have system displacement on this axis. Okay. So I'm going to start with a critically damped system. Okay, so I'm just going to put the blue curve is Q is 0.5 for critical damping, right? So we might see something like this, where we have a relatively quick settling, like so. Contrast this with an overdamp system. So I'll put that guy in red. So this will be Q less than 0.5. So in an overdamp system, it'll just take longer to but get basically the exact same curve. But it takes significantly longer to settle. Finally, in our critically damp system, okay, we're going to have something like this. So it's going to get down to its final value very quickly, but it's going to keep going. So this is the overshoot, and we're going to get this exponentially decaying kind of envelope here. Before it finally settles to its final value. Okay. So in a MEMS accelerometer, the overwhelming majority of the time, we're going to have underdamped systems. Okay. We're going to have underdamped systems because we're largely driving these guys at much, much less than our resonant frequency. Okay. So if we were to look at the step response of an accelerometer, we'll have something akin to this. Okay. So this is going to be time times our linear resonant frequency here on this axis. And our displacement will be up here. Okay. So I'm going to draw two things on this graph. So our input signal, I'm going to put this in blue. So this is the acceleration essentially that we are experiencing. So I'm just going to put a note here. So this is our input. This is our step response. So we very suddenly see a force applied and it's sustained. Okay. Our output signal might look something like this. So it's going to take time for our system to respond to our input. So we're going to see a bit of lagging. We're going to overshoot and ring out like so until we settle to our final value. I'm going to define a quantity here. Actually, tau sub mu is going to be twice q over omega. And this is the time necessary to settle to the final value in our system. Okay. So I'm going to develop a mathematical expression based on the fact that we're dealing with an underdamped system here. Actually, I'm not going to do that because we have 30 seconds left of class. I'm going to do that at the beginning of class on Wednesday. So this is where we'll stop for today.